The March edition of Popular Mechanics reported that the weather of the previous year was strange. Warm. Cities baked under the hot sun and crops wilted as farmers lost $1 million a day. The good old-fashioned winters of years gone by with 15-foot snowdrifts and lasting 6 months were a thing of the past. The author explained to the audience that human emissions of carbon dioxide were causing the planet to warm. This may sound familiar, the kind of reporting we hear all the time now, but this edition wasn't published in 2022. It was published in 1912. For many people, climate change as a topic seemed to appear in 2006 with former American Vice President Al Gore and his documentary An Inconvenient Truth. And while this was certainly when it burst into the mainstream for many people, it was only a late chapter of a scientific story that stretched back centuries. Gore is not an insignificant player in this story, but is by no means the main character. Albert Arnold Gore Jr. enrolled in Harvard College in 1965. During his senior year there, he took a class taught by a scientist named Roger Revelle, who showed his class some intriguing data from a recent experiment. Revelle was a giant. I mean that literally. He was 6'4" with a booming voice, but also scientifically. He was instrumental in the creation of the International Geophysical Year of 1957, was scientific project lead on the study of nuclear detonations on Bikini Atoll, and developed the Scripps Oceanographic Institute in California from having a single research vessel to having a fleet bigger than many countries' navies. He became a huge deal, but started out as a humble PhD student at UC Berkeley in the 1930s, researching how carbon dioxide, or CO2, was absorbed by the world's oceans. The rate of this absorption would turn out to be one of the most significant in the history of science, and Revelle would be the key to its calculation. Why was it so important? Because it determined how much CO2 was present in the Earth's atmosphere. In the late 18th century, scholars were starting to realise that what we call air was actually comprised of multiple gases, notably oxygen and nitrogen, both discovered in the 1770s. Another was carbonic acid gas, what we would now call carbon dioxide. It was first isolated and described a little earlier, in 1757, by Joseph Black, a Scottish physicist and chemist working in Glasgow. Black was quite the researcher. He discovered the element magnesium, as well as the concept of latent heat, the energy required to change the phase of a substance. But apart from discovering it, Black didn't learn much about carbon dioxide, mostly that it immediately extinguished flames that were immersed in the gas. Its most relevant property would be described almost exactly 100 years after its discovery. But before talking about that, we need to take a brief diversion. Jean-Baptiste Joseph Fourier was an interesting character. He was obsessed with heat. He actually believed that heat had life-giving properties, something he picked up when he was forced by Napoleon himself to accompany him on the French invasion of scorching hot Egypt in 1798. Several adventures later, Fourier eventually found himself back in Paris and was able to resume his passion, researching thermodynamics, describing mathematically how heat flows between objects and changes their temperatures. In 1822, he published a seminal book called The Analytical Theory of Heat, which laid the foundations of several key modern scientific concepts, including Fourier transforms and the general equation for how heat flows through an object. The book became rather famous, rightly, but he followed it up in 1827 with a far less well-known publication, a memoir on the temperature of the Earth and planetary spaces, in which he puzzled over the average temperature of the Earth. You see, if you apply Fourier's maths and some other basic thermodynamics to the Earth, you come up with a startling conclusion. You can estimate the average temperature of an object in space, like a planet, by balancing the energy coming in from the sun, in the form of sunlight, with the energy leaving the object due to what we call thermal radiation. The hotter an object is, the more energy it kicks out into space as this radiation. There will be a temperature where the object is just hot enough to emit the same energy as it receives from the sun, what we call its equilibrium temperature. Doing the maths, you find the Earth's equilibrium temperature is minus 16 degrees Celsius. Well, in fact, the Earth has an average temperature of about 15 degrees Celsius. Fourier had various theories about this discrepancy, but eventually decided that the atmosphere must have some insulating property, not reducing energy arriving from the sun, but preventing some thermal radiation from leaving the Earth. This would mean the Earth would need to be slightly warmer to give off enough thermal energy to match that arriving from the sun, maintaining radiative balance. He never found what this insulating property was, though. His obsession with heat's life-giving properties had him constantly wearing multiple thick coats, and the heating in his Parisian apartment turned all the way up. Until, one day in 1830, delirious from overheating, he tripped and fell down the stairs, dying a few days later. Heat, in the end, killed him. As you've probably guessed, the insulating property Fourier was looking for was provided by carbon dioxide, something that was first realised just 2 decades later by a scientist in Connecticut. Eunice Foote was a remarkable figure in the history of science. Raised in New York in the first half of the 19th century, she became engaged with the pressing issues of the day, including campaigning for the abolition of slavery and for the right of women to vote. But she was also an inventor. She invented a paper-making machine, a thermostatically controlled cooking stove, and less squeaky shoes. And she was a scientist. But of course, she was those things in a society in which to be a woman was to be excluded. While she was an inventor, her inventions were patented in her husband's name, as women couldn't defend patents in court. While she was a very capable scientist, it was all but impossible to gain a research position at a university. In fact, she was extraordinarily lucky to be able to take any college-level science classes at all. So when she published Circumstances Affecting the Heat of the Sun's Rays in the American Journal of Science and Arts in 1856, it was the first ever publication by a female author in any scientific journal other than those dedicated to astronomy. She was epoch-shifting, but for more than one reason. In her paper, she detailed experiments she conducted with different gases trapped inside glass cylinders and heated by the sun. She noted that when she filled a cylinder with carbonic acid gas, carbon dioxide, it was heated to a higher temperature by sunlight and, crucially, retained its heat much longer than those cylinders filled with other gases. She correctly identified Fourier's heat-trapping property of the atmosphere. Carbon dioxide didn't obscure sunlight, but it absorbed thermal radiation, and by being present in the atmosphere, even in very modest quantities, this increased the average temperature of the Earth. Chances are, though, that you've not been told about Foote discovering that CO2 traps heat, and how she explicitly stated this warmed the Earth. This discovery was instead for the longest time attributed to the Irish physicist John Tyndall, who seemingly independently recovered the same result with a little more detail in 1861. Though there's some debate about this because Tyndall had, quote, little regard for women's intellectual capability, and so may have just stolen her work and not bothered citing her. Tyndall was much more famous and male than Foote, but making matters worse, Foote's work was mostly lost in a fire at the Smithsonian Institute in 1865, so she was forgotten for most of subsequent history. Her results were only rediscovered in 2011. So while you may have heard of Tyndall, Foote was actually the first person, despite many obstacles, to discover that CO2 kept the Earth warmer than it otherwise would be. However, this graph shows the average CO2 concentration in the atmosphere in a given year. As you can see, it's not constant. It fluctuates year to year, insulating the planet by slightly different amounts, and, according to the theory established by Fourier and Foote, causing its average temperature to change. It was also around now that scientists were for the first time learning about how the average temperature of the planet had changed significantly in the deep past. People like Louis Agassiz and other people who didn't steal their ideas were describing ice ages, periods where the northern hemisphere was much colder than present for prolonged periods, and so the Earth's average temperature was significantly lower. The prevailing view at the time was that the Earth was still cooling down from its red-hot creation, so how, they asked, could it have cooled and then warmed again to present-day temperatures? Some people, including Foote, advocated that changes in CO2 were responsible. More CO2 in the atmosphere meant a warmer Earth, while less CO2 meant a colder Earth. Another person who thought this was Swedish chemist Svante Arrhenius. A child prodigy, in his day job he basically founded what we now call physical chemistry, and for this work won the 1903 Nobel Prize in Chemistry. But he had diverse interests, including climate. In the 1890s, Arrhenius wondered what temperature change would take place if, for some reason, the concentration of carbon dioxide in the Earth's atmosphere halved. This was 1896, and long before this question could be answered fully, with calculations performed by digital computers. But Arrhenius did have one advantage on his side. He was getting divorced. 2 years previously, he had married his student Sophia Rudbeck. Side note, you. And the marriage had not gone well. They were separating. Messily. Arrhenius wanted something, anything, to take his mind off things, so he threw himself into the painstaking, time-consuming pencil and paper calculations approximating how different latitudes would respond to changes in atmospheric CO2, and eventually concluded that the Earth would cool on average by 5 degrees Celsius, enough through various feedback loops to trigger a new ice age. This was an impressive feat, but his colleague Arvid Högbohm wondered something. What if instead of halving CO2 concentrations, you doubled them? Högbohm had compiled estimates of how carbon was cycled through natural geochemical processes, emitted by volcanoes and absorbed by the oceans and so on. Doing this had given him a curious thought. What about estimating how much carbon humans were putting into the atmosphere too? After all, most fuels used by humans are hydrocarbons, structures containing both hydrogen and carbon, most notably wood, oil, and coal. When you burn these things, the combustion reaction releases the carbon previously trapped in the fuel as carbon dioxide gas into the air. If that fuel came from deep within the ground, such as, coal, then you're adding new carbon to the atmosphere. Humans have been burning fuel and putting carbon dioxide into the atmosphere for thousands of years, but on a relatively small scale and not typically using those fossil fuels from deep within the Earth. The 18th and 19th centuries, however, saw an explosion of fuel usage, notably coal being burned to power steam engines after their invention by Thomas Newcomen and refinement by another resident of Glasgow and contemporary of Joseph Black, the discoverer of carbon dioxide, James Watt. By the time Högbohm and Arrhenius were conducting their research, engines descended from those designed by Watt were powering steamships, factories, power plants, and locomotives all over Europe and the Americas, visibly altering the local atmosphere with smog. But all those factories and industrial machines burning coal might add up to something significant on a global scale too, Högbohm thought. After years of analysis, he estimated that humans were adding enough carbon to the atmosphere each year to raise its concentration by 0.1%. He mentioned this to Arrhenius and suggested that maybe in the distant future, humans could double the amount of CO2 in the Earth's atmosphere. At Högbohm's suggestion then, Arrhenius repeated his thermal calculations for an Earth with twice as much CO2, and found that the planet would be 5 or 6 degrees Celsius warmer. Again, feedback loops were at play here. A warmer planet meant more water evaporating into the atmosphere, leading to a more insulated planet, leading to a warmer planet, and so on. He considered this to be a good thing. It would stave off another ice age, but also that this was a hypothetical, something that wouldn't happen for thousands of years. Humans just weren't burning that much fuel. Abstract as they were, his ideas were not taken especially seriously by the academic community. Arrhenius was seen as something of a kook with interests that ranged too broadly to be at all deep outside of his specialism. In particular, the scientific community was dismissive of the idea that human emissions of carbon dioxide could accumulate in the atmosphere. After all, if you leave carbon dioxide and water together, they eventually form carbonic acid. So with the huge surface area of the world's oceans and the relatively tiny concentration of CO2 in the atmosphere, seawater would almost certainly absorb any extra anthropogenic carbon quite quickly. Just 10 years later, though, Popular Mechanics was reporting a general sense that winters were warmer than they used to be. Scientists were warning that European glaciers were melting due to raised temperatures. In 1923, meteorologist Heinrich von Ficker went one step further and warned that a trail of climatic change was occurring from the steppes of Asia to Central Europe, bringing drought and decreased agricultural yields as a result of some global climatic shift. Was extra carbon in the atmosphere responsible for this? Some thought so. Arrhenius' ideas were revisited in the 1930s by British scientist Guy Callendar. In 1938, he published a paper titled The Artificial Production of Carbon Dioxide and Its Influence on Temperature. In it, he estimated that since the end of the 19th century, humans had added an incredible 150,000 million tons of CO2 to the atmosphere, and that this was beyond what the oceans could absorb, so 3/4 of the CO2 emitted by humans was still in the atmosphere. This, Callendar estimated, had warmed the planet by 1/3 of a degree Celsius. However, just like Arrhenius, Callendar believed this was a good thing. It would stave off the, quote, return of the deadly glaciers. Scientists have lost a bit of panache since then, I guess. Maybe future generations would thank us for warming the planet and preventing another ice age. However, also like Arrhenius, Callendar wasn't a specialist in physical climate, instead researching steam for his day job, and so he wasn't taken especially seriously. People still thought that the oceans were easily capable of absorbing any carbon dioxide that humans emitted. While these emissions were real, they weren't going to change the climate. Callendar must be wrong. But some oceanographers were starting to question that assumption. Oceanographers like the giant Roger Revelle, who we met at the beginning. Revelle studied oceanic uptake of carbon dioxide for his PhD, but returned to the subject in the 1950s with his colleague Hans Suess. Motivated by newly invented carbon dating techniques, they re-examined that all-important rate at which oceans absorb carbon, and found that a typical molecule of carbon dioxide emitted into the atmosphere would be absorbed by the oceans in a decade or so. No reason to worry, the oceans would effectively wash away all our emissions before they built up to anything significant. But then, Revelle remembered something from the chemistry he studied in his PhD. Seawater does something called buffering. It's a chemical process that stops the ocean's acidity from rising too much. While seawater might initially absorb a lot of carbon, creating a lot of carbonic acid, eventually buffering will spit much of that carbon back out into the atmosphere. No one had considered this process in the context of carbon dioxide emissions before. So Revelle went back over his calculations and found that in sum, accounting for that eventual spitting out of carbon, the ocean's ability to absorb carbon dioxide had been overestimated by a factor of 9. As an historical aside, Revelle realizing that this buffering mechanism was relevant was a super late addition to the paper he was submitting on the oceanic uptake of carbon. So late that it wasn't included in the typed up manuscript, it was hastily taped to the manuscript with a note. Revelle had found that there was a very real possibility that Callendar and Arrhenius were onto something, and that carbon might be building up in the atmosphere. To find out if this was really taking place, he needed data, and in 1957 he got his wish, the International Geophysical Year. It was a collaboration between scientists all over the world, researching everything from space to the Antarctic to the bottom of the oceans, much of it motivated by the Cold War and the Americans and Soviets wanting to get a military advantage over one another. Revelle was a key figure on the American side of things and was able to secure modest funding for the academic backwater of climate science. He put this money into action, measuring carbon dioxide concentrations over the year with extremely high precision. To accomplish this, he hired a young postdoc named Charles David Keeling. Keeling was a fascinating guy who turned up at exactly the right time in history. Revelle would later say of Keeling that he was a peculiar guy. He wants to measure CO2 in his belly, and he wants to measure it with the greatest precision and the greatest accuracy he possibly can. The benefit of hindsight, thank goodness he turned up when he did. Using expensive new instruments that allowed for unprecedented accuracy, and with a single-minded determination to root out any and all errors, Keeling produced a beautiful dataset of atmospheric CO2 concentrations from Antarctica and Hawaii in 1958. Revelle had planned for that to be that. This was to be a baseline dataset, and someone could take another set of readings in a few decades to determine if CO2 concentrations had in fact changed. But Keeling had other ideas. He wanted to keep going. He scrounged together enough money to keep taking measurements, initially in both Antarctica and Hawaii, but eventually just at Mauna Loa in Hawaii. It became clear after just 2 years that the concentration of CO2 in the atmosphere was indeed increasing year on year. Keeling initially published this result in May 1960, and it was even covered by the New York Times. But people, including Keeling, still weren't worried by this. Keeling himself thought that air pollution was a bigger problem than increasing carbon dioxide concentrations, but advised that we should keep collecting observations in case the rate of increase accelerated. So he kept taking measurements. Scrounging together money wherever he could, he kept measuring the atmospheric CO2 concentration through the 1960s. All the while, signs that the climate was changing started springing up. More crop failures, this time in India and the Soviet Union. People in the global south, Mauritania, Mali, and Chad, noticed persistent changes in weather. More floods, but also more droughts. The CIA in a report in 1974 would say in retrospect that the headlines from around the world told a story still not fully understood, or one we don't want to face. But that the climate change began in 1960. The line, now known as the Keeling curve, kept going up. Carbon was clearly accumulating in the atmosphere. This, by the way, was the data that Revelle shared with his students at Harvard, including a young Al Gore, who would go on to become a senator and secure further funding for Keeling's observations during the tumultuous years of the Reagan administration. Going into the 1970s, as the world population grew and grew more industrialized and urbanized, the quantity of fossil fuels burned every year grew and grew. The engines, originally designed by Watt, were observably changing the atmosphere, and changing it faster and faster. But was this resulting in a change in the global climate? The weather might be weird and crops might be failing, but was the world on average actually warming as Callendar thought? Initially, the answer seemed to be no. Ever since the discovery of past ice ages, scientists were concerned that the freezing conditions might return. As more about past climate was learned through reconstructions based on ice cores and ocean sediments, scientists in the mid-20th century predicted that the natural variability of the planet would make it cool down for the next 20,000 years or so. This would probably be slow, but there was the possibility of rapid cooling over millennia or even centuries back to glaciated conditions. So, when global temperature datasets were constructed in the 1960s and 70s that showed some cooling over recent decades, for some, the alarm bell started to ring. The planet was cooling and tipping into a new ice age already, not warming as some scientists claimed. However, two scientists from New Zealand, Michael Salinger and J.M. Gunn, published a paper in 1975 that pointed out these datasets were dominated by data from the Northern Hemisphere, where most of the scientists were. The Northern Hemisphere may be cooling, but the Southern Hemisphere, according to their work, was in fact warming, and had been consistently since the start of the century. That was significant, because emitting CO2 is only one consequence of burning fuel. The combustion reaction isn't perfect, and so as well as carbon dioxide, unburnt bits of fuel and other compounds like sulfur dioxide are also emitted into the atmosphere. And while carbon dioxide traps thermal radiation and so warms the planet, those other compounds can have the opposite effect, reflecting sunlight away from the Earth and cooling it down. But not just that, because while CO2 is mixed very evenly through the atmosphere, on account of being heavier, those extra combustion products tend to stick close to where the fuel was burned. Scientists like Wallace Brooker and James Hansen argued that in the Northern Hemisphere, the cooling effects of those extra combustion products were outweighing the warming effect of the extra CO2. Hence, cooling as fuel use exploded post-World War II. Meanwhile, in the southern hemisphere, with far, far fewer people and so far, far less fuel being burned, there was basically nothing to mask the warming signal of the globally distributed carbon dioxide. In the scientific literature throughout the 1970s then, there was this debate about which effect, warming or cooling, would win out on a global scale in the end. Were we heading for a scorching future or a snowball Earth? This seeming confusion and division in the scientific ranks was for some evidence that climate science didn't know what it was talking about, and that the so-called global warming effect was based on bunk science. But it's worth noting that at no point in the 1970s did those arguing for human-caused cooling constitute the majority. Global warming was by far the consensus opinion, and by the 1980s, those arguing for net global cooling had changed their stance in light of overwhelming evidence. Thanks to legislation like the US Clean Air Act of 1970, Northern Hemisphere skies gradually cleared of sulfur dioxide and other pollutants. With their cooling effect removed, the temperature trend started moving in one direction: upwards. In some places, the evidence was inarguable, but it would take some time for enough data to be collected and analysed for a judgment on global temperature change to be made. That would be done by several research groups independently. Perhaps most importantly, James Hansen and his influential research group reported in 1980 that the global average temperature had, as a result of combustion products and some natural variability, reached a minimum in the 1960s and had since, by 1980 this is, increased by 0.2 degrees Celsius. Further, while this temperature rise was within natural variability and so swamped by other signals, they predicted unprecedented warming was on the way. It would be clear as day, unmistakably human-caused global warming by the year 2000. And of course, they would be proved right. By the end of the 1970s then, and certainly by the end of the 1980s, the scientific community was in agreement on the physics. Humans burning fossil fuels were raising the concentration of carbon dioxide in the atmosphere, and this was increasing the average temperature of the Earth. While the warming was very modest at the time, it would be significant within a few decades, and spell serious trouble. Society was cottoning on to the danger. The first US president to publicly mention climate change was President Johnson in 1965. The UN, the CIA, fossil fuel companies, and environmental groups were all discussing what to do about a warming Earth throughout the 1960s, 70s, and 80s. So why did it take until the mid-2000s and an inconvenient truth for climate change to become an issue for the electorate and something spoken about in the mainstream? Well, that's a story of the 70s, 80s, and 90s, and it heavily involves Gore, Hansen, and a cast we've yet to meet. Let me know if you'd like to hear it another time. But to finish this story, let me take you back to the very beginning and James Watt. Human emissions of carbon dioxide started to modify our planet's climate with Watt's refinement of the steam engine. The energy his inventions unlocked for use in mining, industry, and transport created the modern world. And as a result, he was somewhat ideated after his death, becoming canonized as the saint of the Industrial Revolution, the man who built the modern world. And, of course, the modern atmosphere. Commemorating his contributions to society, multiple statues were commissioned of Watt, including one for Westminster Abbey in London that was so improbably vast that when it was pulled into the building, it fell through the floor, destroying several rows of ancient gilded coffins in the crypt below. We have made the modern world. Now we have to deal with the consequences and the damage we have done with Watt's legacy. The story of climate change is a story of physics, chemistry and statistics, the building blocks of a huge scientific tower. Normally, you would learn these building blocks through reading textbooks and rote repetition, but this isn't the most effective way to learn. That would be through being guided by an expert through new, interesting concepts, trying your hand at applying them, and developing your knowledge bit by bit through more and more complex interactive exercises. An approach suitable for those in full-time education, similar actually to my experience at Oxford, and those in adult professional life. Well, that just so happens to be how Brilliant works, and they have kindly sponsored this video. Brilliant is an educational website and app built on the concept of interactive exercises across subjects in maths, science, and computer science. This video drew on concepts from their courses in chemistry, waves and light, and solar energy, and I created the graphs using concepts in their course on Python. I've worked with Brilliant as a sponsor longer than any other, and the reason for that is I think their courses are phenomenal. I wish Brilliant had existed when I was learning this stuff in school and university, and if you are in full-time education, I would implore you to check it out. Learning in this way adds a whole extra angle on scientific subjects and helps you understand them faster and more fully. Of course, if you're not in full-time education, then you can use their courses to keep your learning and problem-solving skills sharp, as well as satisfying your intellectual curiosity by diving into a subject you've always wanted to learn more about. Or, of course, a subscription would be a great present for any student in your life. To get one, head to brilliant.org/Simon Clark, where you can sign up for free, and if you would like to get a premium subscription, then the first 200 people to go to that link will get 20% off. Thank you so much to Brilliant for continuing to support this channel and for sponsoring this video. Thank you for watching. The presentation of this video was greatly inspired by the work of BobbyBroccoli, one of the best channels on YouTube. Please go check them out if you've never heard of them. Their videos on the history of physics are fantastic. The content of the video was largely sourced from two books: The Discovery of Global Warming by Spencer R. Wyatt and Our Biggest Experiment by Alice Bell, as well as research conducted for my own book, Firmament. Links to all those will be in the description. If you enjoyed this and would like me to tell the next part of the story, please do let me know in the comments. Please also like the video and share it with others who you think will find it interesting. It really helps the channel out and helps this important history spread further. That just leaves me to say thank you again for watching, and I'll see you in the next one.